Example, we're starting to think about not just single measurements, like single observations. Like, so if you have a single subject from your sample, what's that value and what's the percentile of that one value? But we want to think about the sample as a whole. So this example has to do with sampling distributions. But we'll start out with just a regular normal distribution calculation, and then we'll get into the sample aspect of this. So what is this example? Dishwashers have warranties. In this particular case, the average lifespan, the mean lifespan of a dishwasher is 2.4 years. So that's the population mean. And the standard deviation in that population is 0.5 years. So if we assume that this is normally distributed, and I'm just doing some quick math in my head here, if I add 0.5 and subtract 0.5 to this 2.4, that gives me a range of 1.9 to 2.9. So I added 0.5 and subtracted 0.5. So that range 1.9 to 2.9, 68% of dishwashers are going to live between 1.9 and 2.9 years, presuming that it's really a normal distribution, which is what we're presuming here. Now the warranty, if you're the manufacturer, you want to offer a warranty where your products are probably going to last longer than the warranty, right? You don't want to be replacing products all the time. You want to have the warranty period set so that you know how good your manufacturing is, and the lifetime of the product is longer than the lifetime of the warranty. If you're a company, that's what you want. You want the lifetime of the product to be longer than the lifetime of the warranty so that you don't have to replace it. So in this case, we have some data saying that 68% are in that 1.9 to 2.9 year range, and the warranty is 18 months, which is 1.5 years. That's well under that value. So the company has set their warranty period in a sensible sort of way. But we could still ask the question, what percent of dishwashers will need to be replaced based on this data and assuming that it is normally distributed? So what we want to know is that first is the z-score for this time. Because any dishwasher that lives less than this will need to be replaced. So we find the z-score of the warranty period, 1.5 minus 2.4. So we take the value and subtract the mean and divide by the standard deviation. That gives us the z-score. The z-score is minus 1.8. So value minus mean, divide by standard deviation. That's how you calculate a z-score. This is something we'll use all the time throughout the rest of the semester. So this z-score formula is really important. You want to know and understand it very well. So value minus mean, divide by standard deviation gives us minus 1.8. So then we have to go back to the z-score table, or we could calculate it in Excel, but we can look this one up in the table. Minus 1.8, that's a percentile of 3.6. So 3.6% of dishwashers will fall in that warranty period, or fail in that warranty period, and need to be replaced. Which means that, the rest, the other 96.4% of dishwashers are expected to live longer than the warranty period, and so they won't need to be replaced. Now imagine, so that's the normal distribution applied to a single value. Now we're thinking about the sample. Now we have a 10 dishwasher sample. And now we can think about variation within the sample. If you take 10 dishwashers, from in a random way, there's a chance that you could just get 10 duds, right? You could get 10 dishwashers that are just very, very poorly made, and they all fall in that, less than 18-month lifespan, and all need to be replaced. By chance, that could happen. But how likely is that? What's the variation if you have 10 different dishwashers? Like, so say you were running an apartment building, or you were managing a restaurant, you had dishwashers in different places, and you needed to replace things occasionally. If you're starting to think about a sample of them, what's going to be the variation there? In that case, we want the standard error, which is the standard deviation of the sampling distribution. So if I go back here, a sampling distribution, according to this central limit theorem, is going to be a normal distribution. And the bigger the sample, the more true that statement is. And we call its variation the standard error. And you calculate it by taking this standard deviation in the variable and dividing by the square root of the sample size. So we take the standard deviation for the variable, divide by the square root of the sample size, and that's what we call the standard error, and that measures how much variation there is from one sample to the next. So the sample size goes up, this number is going to go down. When you have a big sample, the variation gets smaller. If you have a small sample, the variation is very big. Okay. So here we take the concepts, I think, here are more difficult than the actual math. The math is pretty straightforward. The math is you take the standard deviation, you divide by the square root of the sample size. So 0.5 is the standard deviation, 10 is the sample size, 0.5 over square root of 10 is 0.16 years. It's what it means that's usually a little more challenging to really wrap your mind around. But what it's giving you is information about the variation in the sample of size 10. And that's a value of 0.16 in this case, which is about 2 months. And so if you have a sample of 10 dishwashers, a one standard error range is about 2 months on either side. So that's a way to think about how much variation there is. Now for the question here, part C, is it possible for the mean lifespan of the 10 dishwashers to be less than the warranty period? So could you get 10 dishwashers that are on average going to have a lifespan of less than 1.5 years? So now we're looking at not where 1.5 years falls on the distribution of all dishwashers, but where it falls on the sampling distribution for 10 dishwashers. So we're comparing this to the mean, just as we did before, but we're not dividing by the standard deviation, we're dividing by the standard error. That's the only change from part A. We're just dividing by the standard error now. And because a sample of 10 is going to have a smaller variation than a sample of 1, this z-score is going to be much larger. And so we get a z-score of minus 5.7, which as far as z-scores go is very large. It's not even on our table. Our table, if we go back to it, only goes up to negative 3.5. So, and that's a percentile of 0.02%. So the likelihood, if you have 10 dishwashers, that the average dishwasher in your sample of 10 won't last 1.5 years is almost zero. Almost no likelihood that will happen. We can't even find it on the table, so it's less than 0.02% chance of that happening. All right, so just to recap here, the data for a variable will have a distribution. That distribution might be a normal distribution. And we've looked at a number of examples where it is. Dishwasher lifespan, that would be one where you expect a normal distribution. But then from there, you can take a sample and look at the value from that sample and look at the distribution of values from different samples. And that's a really important idea in statistical studies, because when you do a statistical study, you're taking a sample and you're making inferences about the population from that sample. So what you need to understand is how much do samples vary from one to the next. And there, what you need to make that comparison is the standard error, which takes the standard deviation of the variable and divides by the square root of the sample size. So in any statistical study, you raise the sample size, you decrease the standard error, and that lowers how much variation there is between samples so that you can be more sure that your sample is representative of the population.